Hi everyone, I welcome you to the presentation of this lecture. Under Signals and Systems, we'll be looking at network realization. So when you're given a network, like this one, Z of S is equal to A plus BS plus 1 over CS. You want to realize such a network, we should take note of the following. Number one, you need to identify the subject. So like the way the equation is here, you need to check the subject to either be an impedance or admittance. So if the subject is impedance, it implies that the additions in there are just telling you that the elements involved are connected in series. If the subject is admittance, they're telling you that the elements involved in there, the plus is showing that they are connected in parallel. That's the first one. Second, you need to know the elements involved in the equation. So you'll be having resistors, inductors, as well as capacitors. So you need to identify, do I have a resistor, do we have an inductor, or do we have a capacitor in such a circuit? And the only way you can identify that with the method I've given here, you'll be identifying elements if the equation is in impedance form. If the subject is impedance, that's when you identify the elements. If it's in admittance, make sure it's in impedance. That's when you will be identifying the elements. If it's in admittance, it's just telling you the connection, telling you that it's parallel. So you need to know these three governing equations. For a purely resistive circuit, you've got voltage, which is in the frequency domain, and current in frequency domain to give us the opposition to the flow, which is resistance. So our impedance for a purely resistive circuit is R, that's your resistance, which is voltage over current. For a purely inductive circuit, voltage over current, the impedance there is SL. And then for a purely capacitive circuit, voltage over current, the impedance involved there is 1 over SC. Once you know these three, then you easily identify the elements in the given network. So for a purely resistive, this is the governing equation telling you the impedance or the opposition to the flow of current in such a circuit. For a purely inductive circuit, the impedance there, it's this which you're having there. For the purely capacitive circuit, it's this one here. So you note these three, then you easily identify the elements in a given set. Let's look at an example. Given the driving point functions, find their simplest realizations. So we want to realize these. Let's start with the first one. So for the first one, just from the previous slide I was saying, I need to identify the subject given. So in here, the subject given, you can see Z of S, which is the impedance. Once you have the impedance, you've got these plus signs, two of them. So it's telling you that you've got three elements connected in series. So these plus are telling you series. Reason being, the subject is impedance. So it's a series combination. The second one is you now to identify what you have in that. What are the elements which are connected in series? So if you look at this one here, you need to note from these. So you'll be able to tell that for the first one, first element here, it's just a 3. And then for these three circuits, you can see the one which doesn't have an S is a resistor. So you're able to tell that you've got a resistor of 3 ohms. So ZS1 will be 3. And then you come to this one. If you are to relate it to this one, the one which has S as the subject is the inductor. So you have an inductor of 2 Henry there. And then for the last one there, the one which has S in the denominator like that, 1 over S of C is a capacitor. Therefore, as you can see from this one here, you've got 3 as the capacitor, 3 farad. Therefore, you've got these three elements, a resistor, an inductor, and a capacitor connected in series. So if you have to draw the circuit, it will come out like that. You've got that, a resistor which is there, connecting an inductor, as well as a capacitor. The order doesn't really matter. Just know that these are connected in series. You have that. So our resistor has a value of 3 ohms, our inductor has a value of 2 Henry, and our capacitor 3 farad. So from there, because the equation was telling you had the impedance, so you have the impedance viewing this circuit from this side, you're having that one there. So this is a very simple example. The equation was already simplified, it was just for us to identify. Let's look at the second one, which is a bit complicated. Okay, we continue with our solutions. So for the second one, that's the equation which we've been given. As you can see in here, you have admittance as our subject now. So subject is admittance and the equation is a bit complicated. So if the equation is complicated, you just be switching it from admittance to impedance. To change it from one form to the other, it's very easy to simplify. So in here, you identify the subject. You're saying the subject is admittance. So what that is telling you is that this and this are connected by a plus, meaning that this arrangement and that arrangement are in parallel. But you need to simplify these and see how they are connected as well. So that's the equation you're having there. Identifying the elements, simplify the given expression to see one element at a time, and then the element should be in impedance form. So from those three governing equations, you have for the resistor, a pure resistive circuit, inductor as well as a capacitor. What we are having here is this equation, the way it is in admittance, let's put it in impedance. Just find the reciprocal of that. When you find the reciprocal, so we are saying these are in parallel the way they are. Simplifying that, we are now having impedance. It was admittance, it's impedance. Impedance is basically the reciprocal of admittance. So when you reciprocate this, it was 1 over 3s plus 2, it becomes 3s plus 2 over 1. Then this one, it was 2s over s squared plus 2. When you reciprocate this, it becomes s squared plus 4. So this one is easier. So this plus is the one which we had initially there. So you're saying these elements here and those elements there are connected in parallel. But here now, there is a plus again. So because our subject here is ZS, this changes now. These two are connected in series. And this one, if we further simplify, it becomes that. This one simplifying. So we have that parallel combination. When we simplify this, it goes to that. So we're just simplifying this expression where you have, there is a plus in there, subject is impedance, it's a series. There is a plus here, subject is impedance, series, but there is parallel because initially it was admittance. So this is what you're having here. Upon simplifying, so here you can't identify, you can identify certain parameters, of course. A 3 here, 3s, because it's impedance, we know that this is an induct. 2 is a resist. In here you've got half s, which is this one here. So this is an inductor as well. But for this one here, it's 2 over s. For us to identify, it should be 1 over s should be in the denominator with a coefficient there. So if you are to get rid of the 2 there, you just say 1 divided by half. Because if you say 1 divided by half, it will still take us to 2. Once that simplification is done, you're having this. And because the subject is impedance here, you can easily identify the parameters. So we've got a resistor of 2, an inductor of 3, another inductor here of 3, and a capacitor of half, or an inductor of half here and a capacitor of half. So this and this are connected in series. Even these two are connected in series. A combination of those two are connected in parallel. So this is what you are having. You have a parallel combination there, which was initially given in the question. But these, because we've broken them down and the subject is impedance, these are series connections. So you've got a series connection of that one, the series connection of that one. Then you can now easily draw the circuit. So you've got an inductor and a resistor connected in series. These are the ones you're having. Then here you've got an inductor and a capacitor connected in series as well. These are the ones you're having. A series combination of this and the series combination of that are connected in parallel. That's what you're having there. So you just put the values there. So there's an inductor of 3 Henry. There is a resistor of that value. You've got that value as your inductor and that value as your capacitor. Then if you are to view from that point, this is what you are having, because initially the equation given was the admittance. So you are viewing an admittance of that much. So you would have realized a given circuit, which is this one. It gives you that. So from that, try and solve the following. So this is a practice question. Given the driving point functions, find their simplest realization. Try out this one as well as that one. Thanks for watching.